As a geologist, I consider the moon to be a planet. It's a small planet orbiting a big planet. So if there's any life on Mars, it's probably, close to a meter or more underneath the surface. It was some of the most thrilling scientific discovery I've ever gotten to be a part of. Let's keep dreaming. Let's keep talking about it. Let's keep talking about the potential for exciting exploration. And there's still a lot more to do with like the sides of moons that we didn't image, say at Neptune or Uranus with the Voyager 2 mission.
Welcome back on the SpaceInfo Podcast. Here we talk about space and everything related to it. If you are passionate about space, astronomy, technology and everything about it, you can join all our social platforms at the SpaceInfo Club or our website at www.spaceinfo.club, where tons of content and a community of experts are there waiting for you. This is the SpaceInfo Club. Okay, so welcome everyone. Today we have Kirby Runyon. Welcome on board. Hello.
Hi, Sebastiano. It's a pleasure to be here. Thank you.
Thanks for joining us. So I'm just letting the people know that you are a planetary geologist at the Planetary Science Institute, also
That's right.
a creative space science consultant and a public speaker, among all the things that you make. So I just leave you the word and present yourself, letting us know what you think, because I'm really excited and I'm really happy to have you here.
Oh, thank you so much. Yeah, just as you said, I'm a research scientist, a PhD research scientist at the Planetary Science Institute, which is a NASA-funded nonprofit research organization here in the United States. But we have people living around the world. But I also have my own company called Planetary Experience, and it's really focused on outer space-themed entertainment, education, and tourism. And so that includes things like not just public speaking, but I also run tours to planetary analog sites in New Mexico, a state in the United States. And also I work with the company Zero Gravity Corporation for outer space themed zero-G flights. And so people can contact me about having some outer space infused at their events. I also work with a company called Galactic Medallion for VIP tours of NASA's Kennedy Space Center in Florida. So I do the serious space research on one side with the Planetary Science Institute, but then I also just do the just for fun space stuff on the side.
Yeah, so that's amazing. And since you're a geologist, I would like to introduce the whole conversation talking about this topic. And maybe you'd like to tell us something about the latest research project in this field.
Sure. So as a planetary geologist, I study rocks, but not rocks so much on Earth. I study the rocky landscapes on the moon and Mars and even places like Venus and Pluto and asteroids. And I've even done some work on some comets. So I've been all over the solar system. But geology is the study of rocky landscapes, and pretty much everything in the solar system that isn't the sun or the four giant planets is a rocky or icy landscape. And so that means that the study of those worlds is the realm of geology. And so most of my research uses images from NASA and international spacecraft that have gone around the solar system. And I analyze, and so the images themselves are my data. And so I do a lot of geologic mapping on the moon. Most of my data there comes from NASA's Lunar Reconnaissance Orbiter, which is basically a spy satellite around the moon. And I've also used images of Mars from Mars Reconnaissance Orbiter, which again, it's a spy satellite around Mars. And that was for my PhD work at Johns Hopkins University, studying the migration of sand dunes on the surface of Mars. But I also do experiments. Geology is also an experimental science. And so I especially study one of the processes that we associate with impact cratering. So a meteoroid or an asteroid hits a planetary surface. All that energy digs a big hole in the ground. It scoops out all that rocky material and throws it across the landscape. And it's that throwing of material, it's that ejecta emplacement that I study with a catapult. And this catapult flings sheets of gravel or sand or even things like crushed up chalk to simulate the material that gets tossed out of a crater as it's being formed. And some of those experiments I do in the reduced gravity of like Mars or the moon or even asteroids using parabolic flight aircraft, the aircraft that fly in a bunch of climbs and dives. And it's not just weightlessness that they can reproduce, they can also reproduce the gravity of the moon and Mars. And so I do that with the company Zero G here in the United States. And that's both really interesting and a lot of fun, and we're starting to get some results out from that. So I study the rocky landscapes around the solar system, and it's a really active area of research.
Yeah. Also, I would bet that some of the people that are listening to us would have say, okay, you're just looking at rocks. They are so they can be small, big, but for sure they don't move. But when you say that they can be ejected into space, this is I think a spectacular image to think about. Also maybe please tell more. But I think that a lot of let's say behaviors of the environment, for example of the moon, can be studied due to impacts of let's say external rocks that are impacting the ground over there. And also I knew that we know with a very high precision, relatively speaking, that the internal part of our satellite is made up of a certain composition, certain materials with some layers, also thanks to the analysis of seismic wave, which on Earth are called earthquakes. Maybe we can call them moonquakes on the moon.
We call them moonquakes.
Okay. So I don't know if you had experience also in this, but maybe you'd like to add some details about this, because I'm very curious about this part.
So anyone listening can go outside with a pair of binoculars or even a small telescope and look at the moon, and you see that the surface is just covered in craters. It's covered in holes in the ground. And so the moon, and I, as a geologist, I consider the moon to be a planet. It's a small planet orbiting a big planet. And the processes of geology apply to the moon just like they apply to Earth. And the really two most dominant geologic processes that affect the beautiful landscapes on the moon are impact cratering. That's meteoroids and asteroids hitting the moon from outside of itself and coming down and hitting it many tens of kilometers per second. But also volcanic eruptions. So all the darker gray areas on the moon that people can see are cooled lava floods, and those lava floods are way bigger than any lava floods we have on Earth. The largest lava floods we have by comparison would be in northern Siberia in Russia, and those were in place, 60 to 70 million years ago. So we haven't seen anywhere near the kind of lava outpouring and erupting onto the surface that the moon had up until about 2 or 3 billion years ago to cover these big gray areas with lava. And then since those lava plains have been in place, it just keeps on getting hit with meteoroids and asteroids of all sizes, forming craters thousands of kilometers in diameter down to microscopic craters that you really need a microscope to see. And you mentioned the interior of the moon that we have, and so the interior of the moon, we think, is very similar to the interior of Earth. And I have a rock sample here. This is from Arizona here in the United States that up until a few thousand years ago had a lot of volcanic eruptions. But the inside of pretty much all the inner solar system's rocky planets is made of this green mineral called olivine.
Oh, wow.
And it's a very iron-rich mineral. If you could go underground hundreds of kilometers, either on the Earth or the moon, and somehow you could see, it would be green. It'd be this really beautiful green color. And sometimes in volcanic eruptions, these green olivine minerals can get attached to the more common volcanic rock, the gray basalt, which is this kind of volcanic rock. This is what is happening, what's erupting in Iceland, in Hawaii, and it's what the majority of the ocean floors on Earth are made out of, from underwater volcanoes. But sometimes this green mineral gets attached and it gets erupted along with the basalt up to the surface. And so that's one of the ways we know what Earth's interior is made out of, in addition to seismic waves, same with the moon. But when we get a rock from deep underground in Earth brought up to the surface, that type of rock is called a xenolith. So if you look at the Latin components of that, xeno, which means alien, and lith, which means rock, it's literally an alien rock, but it's not an alien rock from space. It's an alien rock from deep, deep, deep underground. And in fact, the Apollo astronauts found some rocks, especially on Apollo 17, the last human landing on the moon, with astronaut geologist Dr. Jack Schmidt. Yeah. And they found a similar type of rock called troctolite. And troctolite is sort of like it's like a mashup between the gray basalt and the green olivine, and it's kind of got these greenish yellow olivine crystals mixed in with it. And so lunar troctolites are similar to this green xenolith that came from Arizona. Now, on the moon, we set up the Apollo astronauts set up a number of seismic stations to record moonquakes. And if you have at least 3 seismic stations, and we did, you can triangulate the vibration signals from them, and you can infer how deep is the epicenter, where that moonquake started. And unfortunately, we only collected data up until, I think, 1977 or 79, before someone, unfortunately, at NASA turned them off to save a tiny bit of money. There's no reason they couldn't have lasted well into the 1980s or even longer to collect more data. Yeah, it's frustrating sometimes when space agencies abruptly turn off spacecraft or instruments that are working just fine in order to save a tiny bit of money. It's really not scientifically justified at all. Very frustrating. And so from the little bit of data that we have from the 1970s, when we've reprocessed that data using modern computers, it looks like the moon probably has a small, partially molten iron core, but that is proportionally much smaller than Earth's iron core. But yeah, so volcanoes and impact craters are the main things that control what the landscape of the moon looks like.
Yeah, just incidentally, then to what you said, you mentioned astronaut Schmidt and the last Apollo mission, and I think that for the people that are interested, maybe can read "Failure is Not an Option" by Gene Kranz.
Yes.
And
yes,
he mentions for sure also the other missions, but he gives particular attention to this astronaut, and it is said that he was the first scientist astronaut, differently from the other one who were military pilots, and I think that this last mission also signs the transition from pure space race to something which is more similar to space research. And this is probably the beginning of real science done in space. Then we all know how it ended.
Yeah. No, you're right, Jack Schmitt. I mean, originally, I think it was astronaut Joe Engle was supposed to fly to the moon on the last moon landing, Apollo 17, but he was another military test pilot. Yeah. And sadly for him, but happily for Jack Schmitt and for science, he was replaced on the mission with Jack Schmitt relatively late in the training process. And so we were able to send a trained PhD geologist to the moon. Now, actually starting back on Apollo, all the Apollo astronauts, even starting with Neil Armstrong and Buzz Aldrin on Apollo 11, they had some geology training. And actually Neil Armstrong did very well in his geology training. And while he's an excellent pilot, it's kind of sad he wasn't on a later mission because of how well trained in geology he was. But really starting with Apollo 15 in 1971 with Dave Scott and Jim Irwin, they were not geologists, they were military test pilots, but they excelled at their astronaut geology training. And it was sort of like the equivalent of having, they got the equivalent of a university education in geology. So they may not have had the equivalent of a PhD, but they at least had the equivalent of a bachelor's or an undergraduate degree in geology, and maybe even closer to a master's degree. So they were still very well trained in geology, and science was still the focus of Apollos 15, 16, and 17, what are collectively called the J missions, like the letter J. But Apollo 17 was, we were just getting good at going to the moon and doing science, and then President and Congress cut it, even though we had already built the rockets and the lunar modules for Apollos 18, 19, and 20. So those are sitting in museums now. And fortunately, with the Artemis program that NASA is leading and that a lot of countries have signed on to, we're sending a lot of scientists to the moon. So that's good, that as we're getting ready to go back to the moon for the first time in over 50 years, that we're going to be sending a lot of not just engineers and pilots, but also scientists.
Yeah, and we all hope that now, when you build a new machine, probably you have a nice start and then you stop and then you start again. We hope that now we will start and also keep going at this time. Ben, I'd like to pick up again something that you said at the very beginning to introduce the next topic, and you said that the moon is like a very small planet orbiting around ours. So how do you see the dwarf planets like Pluto in our solar system?
Right.
So what's their function, if we can call like that, and why are they so important?
Yeah, I love your question. Thank you for that. So dwarf planets are planets too, in my opinion. It's right there in the name. Just like giant planets like Jupiter are planets, and terrestrial planets like Earth are planets, we have an adjective describing a noun. We have dwarf or giant or terrestrial describing the noun planet. And Pluto is actually the largest known dwarf planet, and there's 130 Pluto-sized planets beyond Neptune that they don't bother to teach in school. And so really, there's not 8 or 9 planets in our solar system. There's up over 150 planets, and most of them, the overwhelming number of them, are dwarf planets. And they're called dwarf planets just because they're small. A lot of planetary geologists really ignore. We don't use the definition that the International Astronomical Union, the IAU, came up with. It's just not a useful definition, and so we don't use it. And so we just ignore it. And so we use what we call the geophysical planet definition, which just says if something has enough gravity to be round, and it was never a star, like it never underwent nuclear fusion, then it's a planet, regardless of what it's orbiting. And for geologists and geophysicists, that's a very useful scientific definition of planet, because it gets at the geologic complexity. To us, the word planet conveys meaning of geologic complexity. Asteroids are pretty simple, geologically speaking. And as you get much, like really big planets, they start turning into, they accumulate enough gas, they become like Jupiter or Saturn. You get much bigger, you turn into a brown dwarf, which is where the nuclear fusion of deuterium is occurring, and then that's a star. And the inside of stars are actually pretty simple. And so planets are really the most complex. If you use this geophysical planet definition, planets are the most complex, naturally occurring, non-living things in the universe. They've got the most internal complexity. And so those are objects in space between about 10 to the 20th and 10 to the 29th kilograms of mass. Anything smaller than that's an asteroid, anything bigger than that's a star, and therefore simpler.
Sorry, I'm little interrupting you just to give an idea to people who are listening. If I'm not wrong, Earth is something like 10 to the 24 kilogram as an order of magnitude for mass. Am I right?
Right. You're very close. I don't know the exact mass off the top of my number, but the mass of the Earth falls in there, the mass of Jupiter falls in there, the mass of Pluto falls into that, and that 10 to the 20th to 10 to the 29th kilogram range is about the mass that something will turn itself into a sphere because of its own self-gravity. And so for rocky and icy objects, that's around 500 kilometers in diameter, plus or minus, and then up to about Jupiter size. So there's many planets in the solar system, most of which are small. And that's a very insightful realization to have. What's the most common type of star in the universe? It's red dwarf stars, it's M dwarf stars. And they're much smaller than the sun. They have lifetimes around 10 trillion years, much longer than the lifetime of the universe. It's actually the really giant stars, things 50 to 100 solar masses that are very rare, even though they're the most, even though they're the largest. The same is true of asteroids. There's many more small asteroids than large asteroids. There's many more small galaxies than large galaxies. There's many more small rivers than large rivers. And the takeaway message here is that whatever it is we're studying in nature, natural processes always make more of a small number of something than a large number of something. If you took a sledgehammer and hit a rock, you would have a few big pieces, and most of the pieces would be very small. And that happens from atoms. Hydrogen is way more common than uranium, even though uranium is a much larger atom. And that happens to planets, galaxies, stars, asteroids, anything. So I think it's instructive to realize that the most common type of planet, not just in our solar system, but also the universe, are dwarf planets.
Yeah, and this fact that we are talking about geology also when we're talking about the Apollo mission probably introduces us to the third topic that I'd like to discuss with you. I'm very inspired by your words, so maybe you'd like also to share with us your personal experience. Maybe you've been involved in some mission. Maybe you'd like to talk to tell us more about it.
Sure. So I still am involved with NASA's New Horizons mission to the planet Pluto and its planet-sized moon Charon and the Kuiper Belt, and stayed on the mission for the flyby of Arrokoth, this little, I think it's a 30-kilometer, kind of snowman-shaped peanut thing, 1 billion miles, whatever that is in kilometers, further than Pluto. And I actually got to join the mission as a graduate student when I was doing my PhD at Johns Hopkins University. And I was on the Geology and Geophysics Imaging team, GGI. And that was 9 years ago this month, in July of 2015. And, this is robotic exploration at its greatest. Our view of Pluto went from this fuzzy ball that even the Hubble Space Telescope showed us to be fuzzy, to this sharp planet with craters, with mountains, with glaciers, with canyon systems, with dry river channels, probably carved from liquid methane, with these bands of really dark, organic, sooty gunk on the surface. We even saw its methane-rich blue atmosphere as we flew into a solar eclipse, a Plutonian solar eclipse. And I got to be incredibly privileged to see some of the first really high-resolution pictures come down from the spacecraft. Mid-July of 2015. In fact, as far as I know, I got to be the first person to see mountains on Pluto. And there are these, 10,000 foot tall, 3,000 meter tall mountains made out of frozen water, made out of ice, at the southern tip of what we now call Sputnik Planitia, which is this huge impact basin filled with a glacier, but it's not a glacier made out of water ice, out of frozen water. It's a glacier made out of frozen nitrogen. It's very cold. It's about 20 to 25 Kelvin. That's like 25 degrees Celsius above absolute zero. And the gas that is most of the gas that we're breathing, nitrogen, freezes out into a soft solid that can flow very slowly in those cold temperatures of Pluto. And so the hemisphere of Pluto that we flew by with New Horizons is dominated by this enormous nitrogen ice glacier. And so it was some of the most thrilling scientific discovery I've ever gotten to be a part of. And it really scratched a lot of that exploration itch. A lot of the missions that we send to planets and moons around the solar system, we've kind of finished the initial reconnaissance of the solar system from Mercury to Pluto. And there's still a lot more to do with like the sides of moons that we didn't image, say at Neptune or Uranus with the Voyager 2 mission. But at this point, we're sending spacecraft back to places we've already been before. And to keep sending spacecraft to places we've never been before, we need, and not just NASA, but we really need the European Space Agency to do more. We need the JAXA and the South Korea Space Agency to do more of sending spacecraft beyond Neptune to study. There's 130 Pluto-sized dwarf planets out there. I would love to send a spacecraft by every single one of them to see what each of those 130 small planets look like up close. I probably won't get to see that in my whole lifetime, but getting to be on New Horizons, especially so early in my career, is beyond a dream come true. It's just been absolutely thrilling to be part of that ship of discovery.
Yeah, I think that we are all quite lucky to live in this epoch, because a lot of the discovery are going to be done in this field. And I'm challenging all the people that are listening to this episode to write down in the comment what's the revolution period of Pluto, in order to understand how special this mission was. Also because when you hear about launching a spacecraft to Mars, for example, you hear launch windows and terms like that, and people can understand how let's say, special the condition have to be in order to make a launch? Because if you are waiting too much, you can lose that launch window, so you have to wait other months to have again both the planet Earth and Mars in the same in that very specific reciprocal position in order to reach our destination in let's say a decent amount of time. And the more you get out on the borders of the solar system, the more the single revolution periods of the planet or the dwarf planet become high, and also combining this period with the one of our planet become very difficult. And if you want to have a specific launch window, well, this condition become very, very special. So people who are listening, please write down in the comment what's the revolution period of Pluto. And if you think that the public space agency, as Kirby mentioned, will join the forces, let's say, in a smaller amount of time in the future, in order to achieve these scientific discoveries, because I think now I don't want to get into this topic, but probably politics and things like that also interfere a lot into this kind of research. I don't know if you have a different point of view, being so involved in these kind of things, but at least from the outside, this is my point of view.
Yeah, it can be very politically intensive, and there's people with very competing priorities. There's some people who want to prioritize finding life on Mars rather than outer solar system missions. There's some people that want to prioritize going back to Uranus and Neptune instead of going beyond Neptune. And so there's lots of competing priorities among scientists. And yes, scientists can be a very political bunch, unfortunately. But yeah, I mean, with New Horizons, you're talking about windows, and those are really windows of opportunity when you can use the gravity of one planet to get to another. And with New Horizons, we used a gravity slingshot past Jupiter to cut 3 years off the travel time to Pluto. And so you can keep using Jupiter to get to other dwarf planets beyond Neptune, although the opportunity for one planet might only be once every 13 years, or once every 5 years or so. Just because of how Jupiter and your destination might line up. But with larger rockets like the Starship that SpaceX is building, and with the capabilities, and if we get to the point of using very high-powered nuclear reactors in space, that could totally revolutionize how we do distant deep space outer solar system exploration. If you had a nuclear reactor producing, say, 1 kilowatt of electricity, and it was launched on a SpaceX Starship rocket, it might get to Pluto much faster, or another dwarf planet like Makemake or Ixion or Haumea or Eris or Quaoar. There's so many dwarf planets out there. And with, if we're able to get nuclear reactors launched on something like a SpaceX Starship rocket, it's going to revolutionize solar system exploration. So we're sort of in kind of an awkward decade of the 2020s right now, as we're between technological capabilities.
Yeah, because a lot of people they are used to the Earth-like experience. But if you think that 1 kilowatt produced by a nuclear reactor is not that much, actually, 1 kilowatt is less than the power needed by a common house to work with all the things inside. But if you apply constantly that thrust, that amount of power constantly, you can accelerate constantly. Just imagine getting on the motorway and pushing on the throttle constantly. Your speed will increase at every step, so you will reach a gigantic amount of speed, and so you will achieve gigantic distances.
Right.
And also, you mentioned that the word alien at the beginning. I think that some people have triggered at that term. So maybe we'd like to get into the next topic, which is the astrobiology thing and the search of life on other planets. If geology also helps into this, or
yeah. Well, I mean, look, so in the search for life beyond Earth. Geology, the rocky realm, well, that's where, if there's any bugs, any microscopic organisms out there, the rocks are their home, and the rocks are also their food source. They're going to be metabolizing certain nutrients within the rocks, and they're going to be living in the rocks. And so geology is an absolutely fundamental science if you're interested in looking for signs of microbial life elsewhere in the solar system, whether that's Mars or Europa or Enceladus. and not just the shape and location of the rocks, but also what they're made out of, the geochemistry. The geochemistry is very important to look at, because that's the food source for your organisms. And so, of course, there's a possibility that there could be subsurface life on Mars living underneath the soil. Probably not near the surface, because radiation probably would have destroyed any microbial life near the surface. So if there's any life on Mars, it's probably close to a meter or more underneath the surface. I suspect more likely places where there could be life beyond Earth would be in the ocean underneath that icy shell of Jupiter's moon Europa, but also in the liquid water ocean underneath the icy shell of Saturn's moon Enceladus. And I suspect if the space agencies of the world were actually serious about looking for signs of life beyond Earth, the most obvious mission to do would be to fly through the plumes of Enceladus, because Enceladus has these geysers where the ocean is spraying itself into space around Saturn. Would be to fly through those plumes and look for signs of life, like DNA, or something called homochirality of the biomolecules there, or just have a microscope and look for something swimming around. And there was actually a mission concept done by my friend and colleague, Dr. Shannon McKenzie at the Johns Hopkins Applied Physics Lab. It was a mission concept called Orbilander, Enceladus Orbilander, and it would orbit Enceladus, and then it would land on the surface of Enceladus looking for signs of life. And that would be the most straightforward mission to do, to look for signs of life beyond Earth. And that was a report given to the U.S. National Academies of Sciences, and it came in number 2 as the second most important flagship level mission recommended for NASA's portfolio. But if we were really serious about looking for signs of life, it would be number 1. So that mission concept has already been fleshed out, and it just needs $3 billion and some engineers to build it. So. But if you've got $3 billion, we could fly those.
Yeah, maybe the right group of research will look at this video and will say, okay, that's what I want to do. Because I'm understanding that the collaboration, you mentioned the money, probably in a lot of environments, let's say fintech and things like the startups and things like that, is not so difficult to find that amount of money, which is for sure not small, but not extremely large, as some, let's say, financial companies or things like that.
Right.
Probably taking different people coming from different parts of the world with different cultural background to work towards a common goal. And if everyone shares this objective, probably the collaboration is the key to achieve the final goal.
Yeah, that's a big part of it. The problem with, $3 billion, you mentioned, it's a lot, but it's not a lot. It's not a lot for a venture capitalist, but a venture capitalist is looking to make money, and there's no profit incentive, there's no profit motive to do a mission to Enceladus to find life.
That was exactly my point.
Unless you wanted to open like a seafood restaurant and just sell the microorganisms that you'd find. So there's no profit motive, and so that puts us in the realm of philanthropy, and billionaires don't want to donate to that kind of philanthropy, I suppose, and then governments. And so for many political reasons, something like this has not been funded yet, but to me it's one of the most obvious missions to fund if you wanted to, as soon as possible, try to find life beyond Earth.
Yeah, because
I think Enceladus is a much more obvious place to look for life than Mars, for instance.
Yeah, at least when I was studying at the university, I was hearing about these mission concepts about life on some moons, like Enceladus of Saturn, and but they just stayed concepts, and I think that probably there are not much more of these also nowadays. So this is something sad we have to say, but probably that's sad to say, but people always focused on this kind of goals when they strongly need it, when they feel the need of this thing. So probably the public is also part of the whole project to obtain this kind of I wouldn't say funding, but to focus on this mission for a large group of people. I don't know how you see it. Also, engaging the people towards a common goal, for example.
Yeah, I mean that's one area where Space Info Club can help is helping people become informed and enthusiastic. And there's also organizations like the Planetary Society that are you don't have to be a scientist to join. In fact, it's for everyday people to join, and they're international, and they do a lot of talking to government agencies, especially NASA here in the United States, but increasingly also in Canada with the Canadian Space Agency, and hopefully soon with the European Space Agency for its member nations. And really exercising our right as democratic citizens in countries that are democracies, and talking to our elected officials and saying, we want bold, exciting missions to places like Enceladus to look for signs of life there. That's what it takes. And the Planetary Society here in the United States has a really great track record of actually influencing what NASA does based on input from the general public. And I'd love to see that model copied elsewhere in the world, especially in Europe. So, fortunately, in the search for life beyond Earth, the European Space Agency's Jupiter Icy Moons Explorer spacecraft is on its way to the Jupiter system right now to do reconnaissance at both Europa and Ganymede, and also Callisto, but Callisto probably doesn't have as much potential for life. And hopefully this fall, although that's pending some issues with its electronics, the NASA Europa Clipper spacecraft will launch towards Jupiter to do multiple flybys of Europa. And these missions will be initial survey missions to map out Europa and Ganymede at very high resolution, so that in the future we can send landers to Europa and Ganymede and actually dig through the ice and look for signs of microbial life that may have come up from the ocean. Or even more ambitiously, to send submarines, robotic submarines, to Europa and Ganymede and actually swim underwater to look for signs of life currently living in the oceans. But that's unfortunately probably really far out there in the future. And it's too bad, because these same processes, geochemical, maybe biological processes, are also happening at Enceladus, and you don't even have to land on Enceladus. We have a mission concept, and we could go do this at Enceladus. So it would be easier to do this mission at Enceladus, but fortunately, at least, we've got spacecraft on their way to Europa and Ganymede in the Jupiter system.
Yeah, you mentioned the fact of future submarines could swim into that, let's say, water, even though if it is not probably...
No, it's water. It's water.
Okay, so 100% water, maybe...
Yeah, well, it's salt water. It's probably salty ocean water.
Okay. And so even better, and this is kind of a future concept of a mission, and probably a lot of people are getting inspired, also thinking about the future, even though we should think as this kind of exploration as that very same kind of exploration that happened 500 years ago, something like that, here on Earth, when people went from one continent to the other. And even at that time, the amount of people that wanted to explore the globe started from mapping, as we are doing it right now. But the forces that joined at that time were more than the forces that are joining now. A lot of people joined forces to that goal, and they were more than that they are nowadays. But for the few that are willing to think about this, probably they want to get inspired even more thinking about the future. So maybe you want to suggest some topic in this sense.
Wow, I mean,
let us dream.
Yeah, I mean, let's keep dreaming. Let's keep talking about it. Let's keep talking about the potential for exciting exploration in the outer solar system, whether that's looking for signs of life at Enceladus. I mean, people can stay excited and stay informed with Space Info Club, with the Planetary Society, with a lot of these member organizations, and influencing their elected leaders. But for some reason, at least in the United States, that's what I understand the best, is that there is private sector money. There's philanthropic money for ground-based astronomy. So a lot of your listeners may have heard of the Keck telescopes in Hawaii. A lot of the funding, and it's operated in part with the National Science Foundation, which is kind of like NASA. It's a government agency here in the United States that funds science, including ground-based astronomy. But for some reason, there is this precedent for philanthropic donations for science. The Bill Gates Foundation funds healthcare research, including funding universities to do healthcare research. The Keck Foundation funds a lot of science, including astronomy, to be done. And so if that philanthropic model where wealthy individuals could donate money to advance some goal of space exploration, copying the model that's been done very successfully for ground-based astronomy, and just also but pivoting and doing some of that for robotic space exploration of the outer solar system, I don't see why that couldn't be a viable model where governments still contribute a lot of funding, but it would be public-private partnerships. Or philanthropic government agency projects. And so I don't know what it would take for that. I think it's just a cultural shift in the minds of nonprofit organizations and philanthropists. So maybe this podcast will be a small part of that cultural shift of where we put our money.
Yeah, I hope so. Thanks a lot for mentioning it and making it very clear, because that's one of our goals, probably the biggest one and the hardest one. But that's what I want to achieve with this. And also, you mentioned also again a collaboration between the private and public sector. A lot of people prefer to keep speculating from where do those wealthy people get their money, what they want to do with them, but probably sometimes we should instead look at the facts, where those money can get to. For example, to those private organization, non-profit organization, probably that would be the best thing to do in this time. So probably please.
No, that's kind of it, yeah.
And also, okay, you mentioned astronomy and that things, but maybe you would like to mention something like geology and the future of it, because I know that's your favorite field. For those who didn't understand yet.
Yeah, so I just love space. I'm a space cadet, and in university I studied physics, but I'm really terrible at math. I'm really bad at math, and it was actually studying quantum mechanics and the impossible math in quantum mechanics that convinced me to go into planetary geology. Because in geology you can get away with doing a lot less math. There can still be a lot of math, but you can also get away without doing a lot of math. And so geology was a way for me to kind of scratch my space itch scientifically and get away with algebra and light calculus instead of really impossible math. But Earth geology is an interesting example of public-private research. So a lot of our knowledge of Earth's geology comes from the oil, gas, and mineral sectors. We discovered it was an oil company that actually discovered the buried impact crater in the Gulf of Mexico that was formed from the asteroid that helped the dinosaurs go extinct. And it's when geologists do road cuts, when you dynamite a hill away and you put a road through there, you're exposing hundreds of millions of years worth of geologic strata in the wall rock. And I like to say that geology is a forensic science. You can infer what happened in the past by looking at the clues recorded in the rocks, but you have to be able to read the language of geology to understand what the rocks are trying to tell us. And so in my company, I like helping people to experience space and not just learn about it, but actually go out and do something about space. And so I run trips to New Mexico here in the United States where people can look at very planetary or lunar-like landscapes here on Earth. So we go to White Sands National Park, we go to the Carrizozo volcanic lava field in southern New Mexico. We go to some other volcanic places as well.
So please tell us again the name of your company, so people who are interested can look for it on the net.
Yeah, thank you. So my company is, the website is Planex, Planex.space, Planex.space. And so that's, Planex is short for planetary experience. And so the more you get familiar with the geology on Earth that we've learned about from funding for both governments and the private sector, the more you can understand the geology of what's happening on the moon or Mars or even places like Europa. And so Earth is the planet we know best. Earth is the easiest planet to get to. Turns out all you have to do is fall down and you're there. And so by understanding Earth and by if people go on holiday, people go on vacation, you can choose places like national parks where the geology of our planet is on full display. There in Italy, where you are, there's some beautiful volcanoes
Sure.
that can give us insight into the volcanics of places like the Moon and Mars, as well as our own planet Earth. So by understanding the really interesting places on Earth, and they're often places where people don't live, so you have to really travel to get to them. But yeah, so by understanding Earth's geology, you can understand that you can kind of feel like you're on the Moon or feel like you're on Mars without even ever having to leave Earth.
Yeah, you also mentioned that oil and gas company have done some research in that sense because they need it actually. So their straight need into that sense because they have to make money for sure. So they let's say give money to that research. So a lot of different fields can concentrate into research, which can be I wouldn't say spin it off because usually it is the contrary, but can be turn out to be useful in space. And also as we have seen in this episode. The geology, someone can think about it as okay, I'm looking down to my feet to the earth below my feet, but actually it's very useful. It's the basis for space studies. So a lot of different fields can get involved into the overall research. So a lot of people can get inspired to pursue also a career in this sense. Maybe now you have some experience. Would like to tell us some advice in this sense?
Sure. I mean, so for students listening, if space exploration is a field you want to go into, think about geology. Geology doesn't usually come to mind for a lot of people when they think about space exploration. But if you want to study the planets or the moons or meteorites, you can't study those without getting into geology.
And without getting into too much math, I'm understanding.
Yes, well, you can have as much math as you want. If you are very mathematically gifted, there's lots of geophysics you can do. There's lots of very complicated thermodynamics and geochemistry you can do. So the math is there if you want it, but there are also avenues of geology that don't have as much math. But if you're a student, take a look at geology and see if that's a way that you could scratch your space itch. If you think it's too late for you to go back to school, maybe consider geology as a hobby. Get some geology field guide books. Pick out your next vacation spot to be a national park or a volcano. Or here in the U.S. we have state parks, and Canada has provincial parks. And go to some of those places of natural beauty and natural awe and inspiration as you pick your vacation plan. So, and just watch more documentaries on TV. There's some really fantastic like volcano documentaries on the National Geographic Channel. So there's little things you can do in your life to have more outer space and to have more geology in your life.
Yeah, so with this, I'd like to say thank you again. So please, people, visit PlayNext's website and also get in contact with Kirby because he is a force of nature. He's so inspiring. And thanks for being here. Also, if you want, visit the SpaceInfo.club website because a lot of content is so published there. I hope to have you again soon in the podcast. It was amazing to have you here. And I'm so excited about everything you said, and I will go for sure study again all the topics that you said. Thanks for being here.
My pleasure, Sebastiano. Thank you for having me.
See you in the next episode.